Welcome to Chapter 12, Part 2. We are going to discuss equilibrium concentrations and how to solve for equilibrium concentrations using three things. We're going to need a balanced chemical equation. We're going to need an equilibrium expression, which we learned how to write in the last video. And then we're going to create something called an ICE table. I think your book calls it an ICF table, but it means the same thing. We're going to be looking for, initial concentrations, the change, what happens as we go from the initial to the equilibrium, and then we're going to need the end or equilibrium concentrations, which is why I think ICE makes more sense, but they say final, so they use ICF. It's just a matter of style, I suppose. To learn how to use this ICE table, the best way to do it really is to practice while we learn. So this problem that you see right here, it's on this slide, and I'm going to go to a blank sheet so that I have a lot of room to set this problem up, right? It's a little bit of you're going to use some paper when you solve these problems. So we're looking at a specific reaction between H2 gas, I2 gas. It's going to be in equilibrium with the product of 2 moles of hydroiodic gas. Okay. So this is a good balanced equation. So a couple of things we can do here. Maybe I should make this a little bit smaller so that this makes a little bit more sense. Okay, so we have our balanced equation. Before we make our ICE table, move that over just a little bit, ICE. I'm also going to write the balanced equation, the equilibrium expression. So we know that K equals the concentration of the products raised to the stoichiometric coefficients over the concentration of the reactants. So we'll have H2 and I2 on the bottom. We also know, because the problem tells us, that K equals 59.3. So that's going to be helpful later. The temperature, you're not going to use it in the calculations, but K would vary at different temperatures since temperature affects rate and any manner of other issues with equilibrium. Okay, we're also told that initially, so right when we mix these two together, before the reaction has taken place, we have 0.05 molar H2 and I2. So that's our initial concentrations, 0.05 molar. Now at the very beginning, before they've reacted, we have 0 molar HI. Now, we know the equilibrium concentration, but we don't know what that is going to look like. So we do have a balanced stoichiometry here that we can play with. So we know that if we lose X moles of H2, it's 1-to-1 with I2, so we're going to lose the same amount of I2. And it's 2-to-1 with HI, so however much we lose of H or I, we're going to gain twice that amount of HI. Okay, so we know our change. Now, at the end, at equilibrium, we're going to have initial minus X, whatever X was, for both H and I here, since they had the same initial concentration. And then 0 plus 2X is just 2X. So now we have something to work with. So now I'm going to take these equilibrium concentrations and I'm going to plug them in to my equilibrium expression. So again, I know it's 59.3 equals 2X squared. Now, something that you need to be very clear on here, It's not 2x squared. It's the whole 2x is squared. So don't forget those parentheses. It's going to be important. And then we've got 0.05 minus x times 0.05 minus x. Now, we're kind of lucky in this particular reaction because the amounts of H2 and I2 are the same. So I could also write this as 2x squared over 0.05 minus x squared. And instead of foiling this and figuring it out with the quadratic, we don't actually have to do that here because we can take a perfect square root of this. All right, so we could adjust this to solve for x. So we're going to go ahead and we're going to take that square root. We're going to square root everything. So we're going to wind up with 7.70 equals 2x over 0.05x. And now it's a little bit easier algebra. We're just going to move some stuff around. So let's do that. 7.7 times 0.05 minus x. I'm sorry that I messed that up right here. Let me fix that. Minus x equals 2x. Then if we distribute that 7.7, we have 0.385 minus 7.7x equals 2x. Then we're going to add 7.7x to both sides. We're going to see 0.385 equals 9.7x. Now we can actually just solve for x. We're going to get 0.040. This is not the answer. The answer that we're looking for is the equilibrium concentrations. So I'm going to use this and I'm going to go to what I know. I know that the concentration of H2 and I2 are going to be the same, and that at equilibrium they're going to equal 0.05 minus 0.04, right? Because that was x. So equilibrium concentrations for H2 and I2 are 0.01 molar. For HI, it's going to be 2x. So 2 times 0.04 molar, 2 times 0.04 equals 0.08 molar. So it looks like we have more products than reactants, and because K is bigger than 1, that makes sense. All right, so this was a good problem to start with because you always want to double check and make sure that you aren't going to do extra work in your math here. You could have done FOIL and figured this out with the quadratic, but you just didn't need to. So we saved ourselves a lot of time realizing right here that we could just take the square root. Now, what if we can't? What if we can't do that? That is a possibility, and we're going to work a problem now that is going to need the quadratic equation. So again, just to give myself plenty of room because I'm using this iPad to work problems, I'm going to do this problem right here on a blank page. Gosh, dang it. Let's see. Here we go. There's the problem. So we're dealing now with the reaction between chlorine gas, phosphorus trichloride gas, in equilibrium with the product phosphorus pentachloride, also a gas. We are told, well, I guess first I like to go ahead. I know I'm going to write my ice table here, and I'm going to set up an equilibrium expression. I know that my K is going to be equal to PCl5 over Cl2 and PCl3. Everything has an exponent of 1 here. And that is going to equal 33, like we see right here. Okay, now let's fill in our ice table. Now we don't have the same concentrations for both. We have 0.015 molar Cl2, and we have 0.5 molar PCl3. At the beginning, we don't have any PCl5, and so that'll be 0 molar. The change, because this is 1 to 1, will lose the same amount of Cl2 and PCl3, and since it's all 1 to 1, we'll only gain 1 mole or 1x PCl5. So now what are our end concentrations? It's going to be 0.15, sorry, it's 0.015 minus x, 0.05, and I realize I didn't put a 0 in there. There we go. Moles minus x, and then PCl5 will just be x. So now, same as we did in the last problem, we're just going to fill those in, where we're going to have, let's see, I'm going to keep this on the same side I did in my notes, since the math's a little bit trickier on this one. We've got x on top. We have 0.015 minus x times 0.05 minus x on the bottom, and all of that equals 33. Now we're going to go ahead and we're going to kind of work out that bottom part, and so we're going to have x over 0.00075 minus 0.065x plus x squared, and all of that equals 33. Now, we need to rearrange things because to solve using the quadratic, well, we don't want this fraction, and we want one side to be equal to 0. So we're going to rearrange a bit. We're going to have x equals 0.02475 minus 2.145x plus 33x squared. We're going to redistribute that x so that we have 0 on this side. We have 0.02475 minus 3.145x plus 33x squared. And if you just want to rewrite this so that it's what you're used to seeing when you solve quadratics, you could certainly do that. I did it in my notes. It's going to be 33x squared minus 3.145x plus 0.025. And we rounded here, I assume, because the book did. So we're following along with that. All right. Now let's take this and apply it to the quadratic formula. So the quadratic formula is x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. And you're going to fill in a, b, and c. And you guys are going to do that on your own. And because of this plus minus in the quadratic, you actually get two values of x. So you get x is 0.087 or 0.0088. And you have to use some common sense here to decide. So think about what x means. And I'm sorry, I'm a little bit crazy here, but let's go into this little section. I know that the concentration of Cl2 is going to be 0.015 minus x. If I use this value, it's going to be negative, and you will not have a negative concentration. So I'm going to go with the 0.0088. So that's going to, one of the choices will always make sense, and the other one will not if you had two choices there. So I find that my concentration of Cl2 is 0.006 molar. Of PCl3, it's going to be the 0.05 minus 0.0088. So that one is going to equal 0.041 molar. And then PCl5 would be 0.0088 molar. All right, and that is how you could solve one of these problems. It's not as straightforward right? K is 33, so you'd think more products, but because we don't have equal amounts of starting material and it's 1-to-1, what's happening is we just have a lot of excess of PCl3. So the amount that it can move forward is, of course, going to be limited by the amount of that limiting reagent there. So just wanted to explain that since we brought up that value in the last problem. If it's not abundantly clear, you want to practice these types of problems. OWL will give you lots of chance to practice, and I have put up some practice sets on eCampus for you as well. Make sure that you do a few of those, because in the next video, we're going to keep moving, and we'll talk about Le Chatelier's principle in part 3.